All right, rolling audio. Let's do a quick clap.
All right.
Yeah, you don't.
Right.
You guys don't have to do
Oh, I
it.
thought
We have to.
Yeah, no, it's great.
Testing
It's
our
perfect.
mics or
You
something.
want to do it.
Welcome back to AGI's video podcast, or maybe Spacecast, as John coined the term weeks ago. Last time he was here for an episode. Again, long time no see.
Long
Good to
time
see
no
you
see.
again.
I decided to wear the same shirt.
Yeah, you know, it's just, I think you're like Steve Irwin, right? That's
Yeah, it's my
like you have like
uniform.
20 of those in your closet. You just grab them. Me too.
Yeah.
This is that's the same way I get dressed. How about you,
Right.
Mike?
Yeah, actually, I got this shirt out of John's drawer.
Yeah.
This is my third black shirt.
Yeah.
It makes it easier getting ready in the
Exactly.
morning.
It
Yeah,
does.
for sure. John, we were talking earlier. One of the funny stories that I wanted to share was we've actually hitchhiked successfully out of Georgetown together.
And
So
we've lived
we've
to talk about it.
we did. We go way back, John and I.
Yeah.
And we got a ride this is before Uber,
Right.
and we got a ride in the back of a Jeep.
Yeah. We walked up to a couple. There were four of us.
Yep.
My brother, my wife, and you.
Yep.
And me. And we walked up to a couple in a dark alley at night. And
In Georgetown?
In Georgetown.
Yep.
And asked for a ride. And they said, sure.
Right. It worked out. It worked out weirdly okay.
Yeah.
And you were telling a story when we did it, and it was so funny because you didn't even break cadence of the story. You climbed right into the car, and it's like we were just sitting here like talking, and you climbed into the car and the door shut, and it was as if nothing in your environment around you changed. You just kept telling right through the story.
So you don't do this a lot then?
I know. It was once.
Oh, it's just so normal for me to hop into the back of other people's cars.
Yeah, it's
Yes.
for being
With my
abducted or
friends.
whatever. It's
Yes.
great. So thank you again for coming on the show for 6 weeks in a row. And today we wanted to talk to you guys a little bit about the B612 Asteroid Institute. And you guys are very influential and key to that organization, some of the stuff you're doing. And I wanted to hear a little bit about, first, let's talk about the Institute, what it does, because I don't think everybody out there knows. And then let's talk about what you guys are doing for them.
Sure.
Yeah, so there's a non-for-profit group called the B612 Foundation. And B612 do you know where B612 is named from?
I do not.
Yeah, it's from the Little Prince. It's the name of the asteroid that the Little Prince was on. And so for the record, we know of no Little Princes living on any asteroids in our solar system.
Okay.
Okay, for the record. So, I think our official title is we are Institute Astrodynamicists.
I think that's correct. Yes.
For the Asteroid Institute, which is one of the programs from the B612 Foundation. And we've just got a whole group of people. You can go to the webpage, take a look at the Asteroid Institute. Whole group of people there who are interested in understanding asteroid evolution in our solar system, how they go forward, which ones are coming close to the Earth, when you might be able to see them, how you might be able to deflect them. And we've been working with them for several years now.
And the Institute's entire premise is taking responsibility for the future, is the tagline,
Yeah.
together,
Right.
and to protect the Earth
Yeah.
from asteroid
Right.
impacts, which is
Right.
relatively important, I
Yeah.
think, wouldn't you say?
Oh, yeah. Yeah, I would like, I've
Something
got a
we
lot
should-
of friends who were born on Earth, and
Right.
I know they like it
Most of
all,
mine were too, so, yeah.
You know?
It's a place we would all miss, and
Yeah.
and I think it's great that you guys are part of that. I think it's a great foundation.
Yeah, it's some really good people, and what we found. So the different governments of the world, the United States and some of the other governments, they're tracking asteroids really well right now. So there's a Center for Near-Earth Object Studies, the CNEOS, that's run out of JPL. There's the Minor Planet Center, run out part of the Smithsonian, I think, up in Massachusetts, and they have a lot of the asteroid trajectories, and we found a lot of the large asteroids. We haven't found a lot of the small ones yet. And what we're also finding is there are a large number of astronomers and other researchers who are trying to study the dynamics of the asteroid. What is the real population? You know, we see some of the asteroids that we've detected. How many other ones of that size are there, and what orbits is size correlated with orbits, which they don't think so. So there's astronomers, trying to study this. They don't always have the tools to do that. They can get the positions of the asteroids, but then how do they numerically propagate the orbits accurately? There's some open source software out there, and you can download it. It can accurately propagate the orbits if you put in all the numbers correct. And as you know, trying to model high precision orbits, there's a lot of numbers you got to get right. The gravity constants of all the planets of the other asteroids that have gravity, the solar radiation pressure, the Yarkovsky effect. Have you heard about this, Josh?
Nope, I have not. I mean, I did, but I just want to hear you say it. See
Okay,
if you
let's
get
make
it right.
pretend you don't know about this.
Okay, I
right?
don't.
Yeah.
I'm going to pretend I don't know.
So there's this Russian guy back in the 1800s, I guess, right? And he figured that if an asteroid is orbiting the sun, and one side of it is heating, and the asteroid is rotating, that it'll heat up on one side, and as it rotates, it'll emit infrared radiation in the other side and kind of propel it in a different direction.
So it's like turning its engine on.
It's like turning its engine, but it's completely based on the thermal capacity of the asteroid itself, what its spin axis is, and how fast it's rotating. And he's like, yeah, if we ever track asteroids in the future, we need to...
In 2001.
We need to take account of the Yarkovsky effect. And so we've worked with AGI to start modeling the Yarkovsky effect. The JPL takes it into account when they track the asteroids. But if you have a researcher who then wants to see where it would go in the future, you have to model the Yarkovsky effect. And so
it's the outgassing of the asteroid itself.
no, it's actually infrared radiation.
It's infrared.
Yeah,
Okay.
infrared radiation. Yeah.
Yep.
Yeah.
Very cool.
So anyway, so it's been really fun to get into understanding the coordinate systems and everything. But what we're trying to do is make the asteroid orbits and the asteroid dynamics accessible to other researchers who have a background in something else, say astronomy. So we're working with some of the astronomers up at the University of Washington in Seattle, near where Mike is.
Right. So there's some of the folks, like John mentioned, the Minor Planet Center and JPL and that will have their own tools that they use to propagate asteroids. And then if they want to show there's a probability of an asteroid hitting, we're kind of reliant on them to do that and their tools. And so the other astronomers or other folks that are doing this kind of research can make their own tools. But, how do they know the fidelity of their tools compared to what JPL or the Minor Planet Center is doing? So what we want to do is we want to create, through the Asteroid Institute, a set of tools that allows other folks to also do this and have the same fidelity and know that we've tested the system that we put together against JPL and the other folks, and it matches up, using our technology, but make this available to other folks and kind of really democratize that capability.
That's right. Yes, we're democratizing asteroid propagation.
That's right. That's right.
I should hit record more often on the soundboard over here so I can get you guys saying these fun things they
That's
say.
right. That's
Yes.
right. Yeah, exactly.
So
I've been waiting to say that for a long time.
that's right. So
It's on the permanent record now, so good job.
So one of the things we wanted to do were to enable researchers to do studies. Well, what if I had a synthetic asteroid? Not a real one that's going to hit the Earth, but let's say we find one that's going to hit the Earth. Where should I put my telescopes to find it in time that I could launch a rocket and push it out of the way? So that's just a typical research problem. That's one of our use cases. And what we found, in fact, we just did a poster presentation at the Planetary Defense Conference with Sarah Greenstreet. She actually she's one of the astronomers up at UW, and we were supporting her. So she was using this tool we're building called Atom, which is, we'll talk about in a minute.
Yes.
Yeah, and so we're building this tool Atom.
Pull it
What
up
she
right
was
now.
doing is figuring out how much energy you would need to push an asteroid to keep it from hitting the Earth if you found it in time. If you found it 10 years ago, it would take a certain amount of energy. If you found it 20 years ago, it would take less energy. Find it 50 years ago, take even less energy.
And you mean 50 or 20 or 30 years before the impact?
Before impact, yeah. So what we're doing is we're using Atom. We generate a synthetic asteroid that would hit the Earth, and then we use AGI's targeting capability and say, let's apply a small maneuver and see, okay, we purposely put this one to hit Earth. How much would it take to move away from Earth? And one of the cool things we're seeing is some of these asteroids, a statistical population, they will fly close by Earth many times before they would hit. So Apophos is one like this. I think this is actually how you and I started working on this years ago, is modeling Apophos.
That's right.
And so that means there's a gravity assist, which means just a tiny, tiny little nudge. That also means it's very hard to predict where it's going to go. So again, we're trying to make a tool for this. The name of the tool is Atom. It's called the Asteroid Detection and Mapping Program. It's hosted on the Google Cloud Platform. Google is one of our sponsors, and they're enabling us to use the Google Cloud Platform, and for the astrodynamics engine to do all the heavy lifting of the high-precision numerical integration. That's AGI's SDK components. So we're using those in Java on Google Cloud.
Right.
Awesome. So am I going to be able to go in there and log on and create my own synthetic asteroids?
Yeah. So we've put a bunch of open source Python in GitHub, and what our goal is that you could download this Python. You get a login from us, and then as a researcher, you can try running various cases. You want to generate 100 different fake asteroids, and then do some analysis on those, or 10,000. With the cloud platform is super enabling. You can just try a lot of things and see what happens.
Well, and so John talked about the population of asteroids, and so astronomers and researchers will come up with what they think is a reasonable population of asteroids that are going to impact the Earth. And in this case, we had a guy that put together 10,000 asteroids that all would hit the Earth of various sizes and shapes based on his theories about how the population should be. And then we propagated all those back 50 years and said, all right, every step along the way, what would the delta V or energy change require to move those from hitting the Earth? And we found 10% of those were ones that had multiple flybys of the Earth or Venus or Mars.
One was Jupiter, right?
There was a Jupiter one in there as well. And one of the impetuses for doing this is the folks at the University of Washington are involved with a new telescope that's being built called the LSST, which stands for the
Large Synoptic Survey Telescope.
That's right.
This giant telescope down in Chile.
Huge scanning telescope in Chile that's being built for the purpose of seeing changes in the sky. So it's not a Hubble instrument where it looks at particular things and researches those. The LSST's purpose is to scan the sky, I think, that can be seen from Chile like every 4 days. It gets another picture of the entire sky. And so you can see dynamic things that are changing in the sky. And because of that mission and the sensitivity of that telescope, all of a sudden we're going to be discovering a lot more asteroids. And so the folks in the astronomy department at the University of Washington, in looking at what LST is going to do, they believe that a whole lot of more asteroids are going to be detected, and so there's going to have to be an infrastructure, a software infrastructure of some kind to take each of those asteroids and say, oh gosh, does this hit the Earth, and does this one hit the Earth 50 years from now, and so there's a whole lot more data that's going to overflow the system when that comes in.
Yeah.
So something like Atom could be crucial in helping to process that kind of data, and that's why cloud resources and the SDK components become a really important feature for us.
Yeah, and some exciting things are that this same technique can be used by researchers who want, as I mentioned before, well, what would it take to mount a mission to go to that asteroid, either to research it or to deflect it? And a lot of times you might go there, study it, and then try to deflect it after you find out what kind of asteroid it is. So you just want to have these tools out there. And just to reiterate, JPL already does this, but it's not something that a researcher who has an idea can just go and goof around with it. If they try to write their own software, they're going to be bogged down in the gravity constants of the solar system. We're just trying to make it easy to get the right numbers, and say, okay, this orbit already matches. Document, okay, these are the things we did. We're trying to do everything in open source. People can download the Python, can look at our Java, figure out exactly the algorithms we're using. AGI does a great job of documenting all your algorithms, so there's a total transparency there, and just making that accessible. And the other cool thing is by putting this out in open source, that enables innovation. We don't know what other things. So we already know some people are interested in asteroid mining. So this is the same type of thing. You go there, how long would it take to come back? So we've started seeing interested in that, actually. And Luxembourg is actually interested has been looking in that. We've attended some conferences with them.
That's very cool.
And John's wearing a hat right now from Asteroid Day.
I am. My Asteroid Day
Day
hat.
is every June 30th in Luxembourg.
That's right, yeah.
And Asteroid Day, June 30th, is the anniversary of the impact of the Tunguska asteroid in 1908.
1908, yeah. Right. And that thing just flattened the whole forest. And
right.
If something like that happened, that would be a disaster. I just attended, actually we presented a poster at the Planetary Defense Conference. I was attending it, and JPL on the CNEOS website has put up all the slides. They have these synthetic scenarios of what would happen if an asteroid were to hit a city. And this year they said, okay, what if an asteroid was coming to Denver? Now this is a fake thing.
Right.
Exercise only. All the slides are said exercise only. No asteroid is known to come into Denver.
War of the Worlds, radio
right.
panic
Exactly.
kind of thing's going to happen.
But there's some really cool slides there, and they show what would happen if you had an event like Tunguska, but we were just unlucky enough to happen over a city or Chelyabinsk. And,
Right.
and it's always been said, the dinosaurs didn't have a space program.
Right.
Well, the just the numbers on that is that incident was a 50 to 100 meter wide asteroid, and it had a 2,000 square kilometer part of the forest that was destroyed and flattened 80 million trees.
Right.
Yeah.
So it's not little
No.
at all.
Not
No,
at
if
all.
that happens over New York City or a big metropolitan area, you kill people. So
And that's not even that big
No.
size for the asteroid.
That's a small one.
Right.
In fact, right now, I think the plan is to document 90% of the ones just down to 150 meters,
Right.
something like that.
So that's below that even.
Yeah, this is
Right.
even below that. And so, again, that's what we're doing with the B612 Foundation is looking at what are the smaller ones and how would we detect them. So using ATOM, you could pose the question, well, if I put these telescopes around the Earth, how many of the smaller ones would I see? Because using satellite toolkit components, SDK components, we can calculate the light curve and see at what time do you start seeing it, how long is it tracked? Or what if I wanted to fly a telescope in space or a fleet of telescopes? If I put it near the Earth or Venus or Mars, when do I increase the probability of detection? These are research questions that we want to enable, and that's why we're building ATOM.
Is there going to be a minimum threshold for decision to act upon an asteroid? Have you talked about that at all?
Well, so that's what this Planetary Defense Conference is doing. It's really exciting. Again, all the slides they are posted on the website, and they go through that. And that was one of the arguments between the teams. They do a mock evacuation.
FEMA's there. Yeah.
FEMA's there. It's like, what would happen? And they had a group that was representing the citizens of a city, and they had a group representing the decision makers. And let's go through that argument. Why didn't you tell us when you first knew about this? Well, we didn't want to do panic. Well, thanks. I just bought real estate there, and now I have to evacuate. I'm not coming back. And they're trying to just get this all about our system and what are the decision-making process. Not everyone's the greatest actor, but it was really fun. But for me, I learned a lot. It's like, boy, if this were to happen, this is a lot different than the movies. Now, we can always just get Bruce Willis to go
I would
save
trust
that.
Bruce,
Yeah,
probably.
I would,
I
yeah.
mean, he would
should
do
invite-
something.
Does he get invited to these conferences?
I don't know why he's not.
Should be invited.
Yeah, that's right. That's right.
It's a message to you, Bruce. We want you to come to
Yeah.
the next
Yeah,
Planetary
come to the
Defense
next one?
Conference,
Yeah.
2020.
Yeah, that's right. That's right.
So how many years do you think until something could actually be done in defensive purposes?
Well, so this is the weird part of understanding asteroids. So it's statistically unlikely.
Sure.
However, the ramifications are really, really bad. So the example I use is you fill a football stadium with people. Okay, so how many people in the Seattle Seahawks stadium?
65,000.
65,000. Okay, so put me in the center, put a blindfold on me, and give me a bow and arrow. And
Are we actually going to do this?
No, this is exercise
Hypothetical.
only.
Exercise only.
Yeah.
All right, it's good.
You spin me around,
Right.
and I just shoot the bow and arrow. You wouldn't let me do that. I mean,
No.
the odds of it's less than 1 in 60,000. I'll probably hit the ground. I mean, it's very low probability I'd hit anyone. But it's the consequences of getting hit by an arrow are so bad, you wouldn't do it. And that, in my mind, that's what I feel about the asteroids is, yeah, it's low probability, but if this happens, we don't want to do that. I live in Ellicott City, Maryland, and we just had 2 1,000-year floods in 2 years.
In 2 years.
Yeah. So thank you, statistics.
Right.
So again, so it's almost not what the odds are. It's what risk do you want to tolerate, and why don't we just be prepared?
Right.
Right, and if you have the ability to avoid the risk,
Yeah.
it's responsible to do something about it.
And kind of
So you're really taking a research-based approach to being prepared for something statistically
Yeah.
unlikely that could be very bad for most
Yeah.
people on the planet.
And the cool thing is we now have extremely powerful rockets. We have a capability to fly these. We're, flying, to asteroids right now and studying them.
Mm-hmm.
So it doesn't mean we have to stop everything and just build up a capability to do it. Let's make sure the capabilities we are building to go do science or asteroid mining, those could also be used for planetary protection. And I think things are going in the right direction.
Well, and that's, of course, is what we're doing parallels all that, because we do have cloud computing and we do have SDK components and we have the ability to do this analysis. So let's do it. Let's put those tools together, put the other tools together, and take advantage of the technology we do have and be ready for this kind of thing.
Yeah.
That's awesome. Well, we appreciate your work on it. I think it's going to pay off for all of us.
Well, thank you for the software. I mean, seriously, you're enabling it. It's cool.
Thank you. Thanks, guys. That's it for this time. Next time, John and Mike will unfortunately not be with us, but we really appreciate them coming here and doing several of these in a row, all on different days, obviously.
Of course. Very good.
Thanks, guys.
Thanks a lot.